Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. If you've got a small time series problem, maybe something that fits on your machine, you can load it all in memory, just a univariate system, you can throw a ton of compute power at it. Run every model you'd like. There's some great libraries, we've covered a couple of them on the show. Those libraries give you a common interface to many different time series techniques, and you can throw the kitchen sink at your problem. However, if you want to scale that process up, there are several problems you're going to bump into along the way, one of them being the cost. Everyone is familiar with optimizing for accuracy, but what about a trade-off between accuracy and cost? And you know what? Maybe that trade-off isn't much of a trade-off at all. The recent paper Fast and Frugal Time Series Forecast gives some excellent suggestions for time series at scale. Today I interview Fotios Petropoulos about time series on big data sets.
I am Fotios Petropoulos and I am Professor of Management Science at the University of Bath in UK. My research focuses on forecasting and mostly time series forecasting, both from a statistical and behavioral point of view. So overall, my focus is to improve forecasting processes, both by improving the statistical underlying approaches, but also integrating managerial judgment in the best way.
We've been doing a number of episodes on time series, and I hope I've given some good treatment to the statistical aspects, talking about algorithms and methods, but I don't know that I've really covered the behavioral side. Could you delve into what you mean by that?
Yes, so the behavioral aspect of forecasting has always been there because it's mostly from the human perspective that we want to have ownership and control over everything. And managerial judgment can be integrated in forecasting in several ways, from completely abandoning the statistical process and producing a fully judgmental forecast. For example, having a statistical output and revising it using judgment, or even applying judgment in particular aspects such as which statistical model we are applying, or even what parameters or hyperparameters this model should have.
I come at this from a bit of more of the machine learning and statistical side, where I guess I'd like to presume that my work is the most important part, and the idea of someone taking the forecast and then tweaking it makes me a little nervous that they may not understand it or may tweak it in the wrong way. I'm even reminded of the famous Isaac Asimov story, where there are a series of people making judgment calls, and then the general flips a coin at the end to decide if he follows it or not. Are there any cautionary tales here for when expert judgment is at play on the output of a forecast?
Yes, there has been a lot of research in this area, and some of the names published a lot include Robert Files and Paul Goodwin and Nigel Harvey, all of them based in the UK. The idea is that more often than not, applying judgment can be harmful to the forecast accuracy, but equally, if there is significant information with the managers that is not available with the system, with the forecast, then it might be the case that such interventions might be beneficial. Generally speaking, research has shown that when adjustments are made in a significant manner, then it's more likely than not that they will be beneficial. Whereas we see a lot of times that humans just tweak with the forecast a little bit, so they make 105, 106, and some of the times they do that just to justify, their jobs, their tasks, if you wish, their roles in the forecasting process, so that nobody can tell them, so what have you been doing all day?
Well, when I review a lot of time series literature, I seem to find most people highly focused on accuracy as the golden metric you want to shoot for. But I learned from your paper, Fast and Frugal Time Series Forecasting, there are certainly some other good things to consider when evaluating how to approach a time series problem. Could you share some insights about what organizations care about beyond accuracy?
So there are two aspects that are not widely represented when it comes to evaluating forecasts. And as you say, mostly people are focusing on the accuracy of the forecasts. And within that sphere, I would also include the less frequent cases where the focus is on the uncertainty of the forecasts, the uncertainty surrounding the forecast. So if you wish, we evaluate the forecast directly, either when it comes to how accurate the point forecast is or how good the prediction intervals are. But I don't think we should stop just there. There are two other aspects that are of equal importance. And the first one is the cost of the forecast error. So that is 1% of accuracy. How much does it translate to utility? Either this is inventory, stock holding, or customer service level, or anything else. And the other aspect that we particularly discuss in this paper that you mentioned is the aspect of the cost of the forecast itself, where we focus on the cost that it's needed to produce the forecast. And when we talk about producing the forecast, here we can consider, for instance, how computational intensive some statistical or machine learning methods are, so how long it takes to actually run the methods, the algorithms, and produce forecasts. But also from a judgmental perspective, the cost of the forecast translates to how many humans do we need, how many demand planners or managers we need to take care of the forecasts or to apply judgmental interventions, and so on and so forth.
Yeah, I'm very interested in that third, well, both categories, but maybe we can unpack the third to begin with, the cost to produce it. I suppose if I went to some head of HR and asked them to come up with a smart way of measuring the staff that are committed to some time series work, we could probably get a human power in terms of hours or person days or something along those lines. But the computational cost is challenging to get at. Can you elaborate on what you're going to measure in terms of the compute costs to do the work?
Yes, first of all, let me put this into context because the computational cost might not be relevant for many organizations when they deal with a few hundred of time series, but it becomes quite relevant in a retail context where we have several hundreds of thousands of stock keeping units, SKUs, and at the same time we have several thousands of stores. So the combination of unique SKUs and stores is usually in the region of millions or even billions sometimes, for instance, for Walmart or Target. So when you have such a massive number of time series, and nowadays you usually have to produce forecasts quite frequently, for the fresh produce it might be even twice a day that you need to produce forecasts, you can imagine that the computational burden is quite relevant here. Producing forecasts for a single time series, it might take half a second using standard statistical methods, but if you multiply this half second with billions of SKUs, billions of time series, then this becomes problematic. And usually companies use web services to produce these forecasts. So all of this comes to a cost that is effectively measurable.
Yeah, I can see if I have to do so many of these time series forecasts, half a second or however long it takes times a billion is a lot. But why can't I just lean into the cloud and do it all massively parallel?
You can, but still, this again comes to a cost, right? So you could rent Amazon Web Services, a big cluster, but at the end of the month, Amazon will send you a bill for the usage of that. And of course, the more you have consumed, the bigger the bill is. The point here of our research is how we can effectively minimize this cost of the computation for producing statistical forecast, however, without harming the forecast accuracy. So keeping the forecast accuracy the same, if not better, but at the same time making the computational burden less.
In some ways, that sounds like a free lunch. What's the secret behind it?
Well, the secret behind it is that there are so many models nowadays in our attempt as academics to capture every possible pattern that exists out there, every possible data generation process. We have devised over the years all these many different models, all these many different variations of exponential smoothing or ARIMA models. And the fact is that if we even were in a position to select the best model and the best parameters, nobody could guarantee us that this particular model and set of parameters would be still the best in the future. So even if this is the best with the data we have, maybe another model will be the best to produce good forecasts. So my point is that we don't really need all this large number of models, either in the exponential smoothing family or in the ARIMA family. So using less models and still being able to capture the basic time series patterns, that is trend and seasonality, then effectively your search for optimality decreases and you have a good enough model to produce good enough forecasts for whatever comes ahead, which you don't know whether this might be the same as before the pattern or it might be something that changes. And of course, this line of research, if you wish, goes back in the 80s with the work of Spyros Makridakis and the forecasting competitions back then where he showed back then that simple exponential smoothing models can effectively outperform the state-of-the-art back then, which was ARIMA, Box and Jenkins model. However, since then, the exponential smoothing family increased a lot in size. So back then we have maybe a handful of models, and nowadays we have 30 different exponential smoothing models. And that's exactly my point. Do we need all of these models? Do we really need, or if you wish, are we able to differentiate between a certain combination of trend and seasonality, that is, let's say, multiplicative trend with additive seasonality, or multiplicative seasonality with additive trend, and so on and so forth? Or maybe we should just have a set of simple models that collectively can cover all these different forecast profiles and thus decrease the computational cost, the search for an optimal model, if you wish. So the whole research lies in the lines of simplicity. So simple models could produce good results, even better results from more complicated models, but also lies in the sphere of suboptimality, which is effectively, even if your model or your parameters are suboptimal, then this will not necessarily harm the forecast accuracy, because optimal or suboptimal, this categorization is based on the current data, and future data might not be the same as the current data.
The idea of a simpler model is very intuitively appealing to me. I think Occam's razor is a good heuristic, but I'm curious how you measure simplicity, or maybe you measure its inverse, complexity. How do you know how simple or complex a particular model is?
In this particular case, we explore two different families of models, and I think we take a different approach when it comes to this between exponential smoothing and ARIMA. I will start with ARIMA, which is more straightforward. A more complex ARIMA model is a model with a higher degree of parameters. So in ARIMA, we have autoregressive and moving average components, and you may have several orders autoregressive and at the same time several orders of moving average. And our findings say that when it comes to yearly and quarterly data, a maximum order of 1 or 2 is enough to achieve the best performance, either in terms of point forecast accuracy or uncertainty, but at the same time, the least computational cost. So for a ARIMA family of models, the complexity essentially is measured by the order of the model. In the exponential smoothing, though, there we have 3 components, if you wish. We have level, trend, and seasonality. And while we don't decrease the number of components, what we do, we try to reduce the number of models through which our algorithm goes. So instead of going through all 30 models of exponential smoothing, we define a reduced set of models which contains 8 models. And these models can cover all the forecasting profiles when it comes to trend and seasonality.
Could you elaborate on what those 8 models are and why they were selected as the 8 of choice?
So we have 8 exponential smoothing models in our reduced set, and these are a model that contains only level, no trend or seasonality, a model that contains trend, a model with seasonality, and a model with trend and seasonality. And here effectively we have 4 models, and then we have another 4 models for a multiplicative type of error. So we have 4 models for additive type of error and 4 models for the multiplicative type of error. Overall, models that we exclude are models with multiplicative trends, which have shown to have explosive forecasts, and also we exclude models where the type of the error does not match the type of the seasonality.
Well, if you're able to get pretty good, if not better, forecasts without using any multiplicative trends, it almost implies that set of research or things working with that area aren't adding a lot of value to the big picture here. Is there some trade-off I'm not seeing? Are you maybe making your approach not applicable to some niche area? How can you get by without this popular technique?
Well, I think that including multiplicative trends from a theoretical perspective makes sense and makes, if you wish, the whole exponential smoothing framework more complete. At the same time, though, the exclusion of multiplicative trends is something that Rob Hyman and I discussed, I think it was 2015 or 2016. And after our discussions, Rob Hyman revised his very popular forecast package for our statistical software to set the ETS function which produces forecasts for exponential smoothing so that multiplicative trends are excluded by default. We experimented with some M competition data, Makritakis competition data. We saw that excluding multiplicative trends actually brings us better results. So, as I said, I think the same argument goes back to the 70s or 80s, where back then everybody believed that ARIMA models, box-Jenkins models were much better than exponential smoothing models because they are theoretically more sound and more complete, and theoretically are able to capture every data generation process. However, still back then, empirical investigations show that simpler methods, such as exponential smoothing, can bring better results.
The following message comes from Data IQ, the platform for everyday AI. The potential for positive change with AI is huge, but seeing that value is hard. It's about organizational transformation, not just technology. And today's businesses struggle with the complexities of bringing AI innovation to fruition. That is where Data IQ comes in, bridging the gap between all of the challenges and tensions present to infuse a culture of working with data and AI every day and at every level of the company. Whether solving for the mundane, like automated forecasting, or what is the optimal number of widgets to buy, or undertaking moonshots that push the limits of today's technology to grow your organization and innovate. Join more than 45,000 people worldwide across banking, insurance, pharmaceuticals, manufacturing, retail, and more, who are driving exponential results with Data IQ. Visit dataiq.com, DATAIKU, to learn more. Time spent searching for and interviewing candidates can take time away from managing and growing your business. That's why LinkedIn Jobs has made it easier to get the candidates worth interviewing faster. And it's free. Look, for me, the unit economics on this are very simple. Basically, everybody's on LinkedIn. Everybody I want to hire. I want to draw from the biggest pool of people I can find, and I want to whittle that down fast. I don't want to waste your time or have you waste mine. LinkedIn Jobs makes that easy to do, and like I said, it's free. Create a free job posting in minutes on LinkedIn Jobs to reach your network and beyond to the world's largest professional network of over 770 million people. Focus on candidates with the skill and experience you need. Use screener questions to get your role in front of only the most qualified people. Then, use simple tools on LinkedIn Jobs to quickly filter and prioritize who you'd like to interview and hire. It's why small businesses rate LinkedIn Jobs #1 in delivering quality hires versus leading competitors. LinkedIn Jobs helps you find candidates worth interviewing faster. Did you know every week nearly 40 million job seekers visit LinkedIn? Post your job for free at linkedin.com/dataskeptic. That's linkedin.com/dataskeptic to post your job for free. Terms and conditions apply. If I had some very small data, maybe a time series, a univariate time series of 2 years of data, I probably could use just about any technique and not bump into too much trouble. But I definitely see a lot of problem points coming up if I try and scale that, for example, to your Walmart example. In fact, the paper estimates some of the costs of doing forecasts across all their SKUs, and it's something astronomical, right? It's a 6-figure cost just to do a forecast for all of them. So certainly industry must be looking at the cost-benefit trade-offs. Do you have any insight into how general industry practitioners look at a problem like this?
Yeah, I mean, if you have just a few time series to forecast, maybe you don't even need to forecast. Maybe, let's say, you need to pick up the phone and ask your main distributors what is their forecast, and then sum them up. Maybe it is as simple as that in some cases. Or in other cases, it might be better to, if you have just a few time series to forecast, to actively look for indications that you can include in the time series, potentially some causal variables, or even applying judgment. But all of these things cannot happen when you have to deal with hundreds of thousands of time series, obviously. So as you correctly said, I think that the problem we're touching here might be more applicable for retailing contexts where scale matters a lot. And there is a very nice article by Philip Gerald, I think the name is, who used to work back with Target. And he was saying that, they were applying simple linear models, linear regression models, using some fancy computer architectures just to produce forecasts as fast as possible. But as you correctly say, this might not be the case if you have 2 years of data, of monthly data, for 100 of time series, and you want to produce forecasts every month or so. You have all the time you want to do that. Still though, the aspect of the cost of the forecast when we produce the forecast hasn't been investigated a lot. And here we only touch one aspect of this, which is the computational aspect. But I think there are so many other aspects to touch, such as what is the cost of involving humans in the whole task. And here I'm referring to the actual cost of humans, not consequent benefit in forecast accuracy per se.
Yeah, could you elaborate on what the human participant is doing there? Is this just a code monkey who's got to type everything in, or is there some intellectual process to the work as well?
This goes back to our earlier discussion. I wouldn't see that it's a code monkey. I wouldn't see the human there as a data scientist. I would see as a person who is using some developed forecasting package. Either this is in-house or is bought from an organization. And they're using this package to produce statistical forecasts. And then they revise these forecasts so that potentially they integrate other factors that have not been considered by the algorithm.
I'm a little hung up on the idea that the simpler models could be as good or better than some of the more complex ones, because I know that complexity often, if nothing else, will allow other models to overfit the data, which doesn't mean it's a very good model, but it wins the contest in some sense. Do you have a perspective on why, when you look at something like the M competitions, how all the more complex techniques aren't, getting paces ahead? What is it that they've overcomplicated things around?
There's been some change over the years when it comes to the results of the M competitions. In the early competitions, let's start with M3, which is one of the most famous forecasting competitions, which ran in 2000. Neural network techniques didn't perform very well. Statistical methods effectively dominated that competition. In the next iteration, which was M4, 18 years after, we saw some ML-type approaches. So the winning approach was an approach that effectively combined statistical aspects, a Holt-Winters exponential smoothing method, with some neural network aspects. That was the winning submission by Slawek-Smil. And also other submissions in that competition show some indication that if we do smart integration of machine learning into statistical methods, then we might achieve better results. The picture in the M5 was a bit different. In the latest M5 competition, which dealt with retail data, in fact, from Walmart, we saw that ML approaches, and in particular an approach that is called light GBM, the approach that dominated light GBM stands for light gradient boosting machine learning method. It was the approach that dominated the results in the M5 competition. However, if we see the results of the M5 competition a little bit more carefully, then we will realize that this outperformance of machine learning over statistical methods is not consistent across different hierarchical levels. So machine learning methods were much better in predicting the higher levels of aggregation, where we have just a few time series. Whereas when it comes to the lower levels of aggregation, where we have the majority of our time series, where we have our data in the most granular form, SKU multiplied by stores, on that particular level, the difference in performance between machine learning and statistical methods was very minimal. I think it was about 1 or 2%. So given that, and given the very, very big difference in the cost, time-wise, computational-wise, of running light GBM methods and running statistical methods, such as exponential smoothing, then the argument still applies. So we don't yet have a direct comparison of the two. And one problem that we don't have that is an ongoing discussion between, let's say, the statistical and machine learning community with regards to how often models should be updated. Because one of the arguments from machine learning is that most of the time needed for computational-wise is to train the model. And once you have the model trained, then it's quite fast to produce forecasts. However, how long can you keep the same machine learning model before you need to actually update again? this is an argument, it's a question that we don't have a clear indication for. So do we need to update it every day, every 10 days, every week, every month, every year? We don't have a good answer to this question.
Well, every time the data generating process changes, right?
Yeah, but if you wish, exactly the same reply would apply to the statistical method. Do you need to rerun exponential smoothing models and fit the parameters every period? Or do you need to do that only if and when the data generation process changes? So my argument is that if you don't need the whole computational cost for machine learning methods every period, equally, you don't need it for exponential smoothing either. So still, if we put all of this together, still we can have the same level of performance where in the aggregation levels, in the hierarchical aggregation levels where scale is an issue, in a much, much lower computational cost.
Yeah, it's the issues of scale that are very interesting to me, and I love the thoughts that the paper shares around a big retailer, that if you do the combinatorics of how many SKUs they have times how many stores, it's this massive amount of product time series that they might want to forecast. But it also occurs to me that that's a pretty diverse, maybe even long tail set of time series. At some large retailer, I'm sure they have hot items that they sell once per hour, maybe once per minute at big stores, yet there are some items that they might sell one a week. Do you think there's a one-size-fits-all approach that's good to cover these cases, or should some sort of distinction be made between based on frequency or heteroskedasticity or some metric like that?
Yes, absolutely. I think the problem here, the problem of calculating the cost of producing the forecast becomes more relevant as the frequency of updating the forecast increases. So we wouldn't really bother potentially about this for frozen goods or goods that can last for long or goods that we potentially order once every year. But it would potentially be the issue when it comes to fast-moving consumer goods that you need to produce forecasts for potentially every day or even every week. In computing our numbers and we make some assumptions in the paper to show the scale of the problem from a monetary perspective. And in doing so, we only assume that we take 1% of the total number of items that Walmart would have to forecast. And only with using this 1% of the number of items of Walmart, then potentially we could see some savings of close to $2 million annually, only from saving computational time and without harming forecast accuracy.
Yeah, the cost-saving angle is a big deal for large organizations. For a long time, just cloud cost in general was a problem, but we've seen a lot of tools emerge to help people measure their costs and reduce it. There's tons of companies that have spun up around this. But I don't know of anyone who will help me decide the amount to allocate or even give me a good tool for allocation of resources towards forecasting. What do you see as the practical steps for organizations to leverage some of your research and get their costs in line with the value they derive from the forecasts?
I think it's hard to put a number on it per se, but I think one has to consider several aspects when it comes to that. I think here we only touch to a very particular aspect of the problem, which is the cost of running the forecast. But before even we go there, there are several other costs that need to be considered to build your forecasting engine. For instance, when it comes to choices for forecasting software, if you're going to develop something in-house, or you're going to rely to an open source solution, or you're going to purchase a solution from another enterprise, or even if you're going to outsource the forecasting task altogether. This is one thing. Then the other thing is about the team that you have to produce the forecasts. So, and now I'm not referring necessarily to the data science aspect of the issue, but mostly to the demand planning aspect of the problem. And then, of course, you have to think about what do I go with? Do I go with a trend, which is machine learning, because this is what everybody goes with? And do I go with that blindly without even doing analysis on my own data? Or should I start with a status quo and start a forecast value added approach, start with a simple approach, even naive forecasting, and then slowly starting upgrading this to exponential smoothing, to potentially machine learning, but keeping track on the improved accuracy and trading this off with the additional computational cost required to produce the forecast. So effectively, I think each organization needs to find a trade-off, because one particular issue here is that we cannot, as a rule of thumb, put a value in 1% increase or decrease in forecast accuracy. This is very context specific and area specific. So I think the best way to go for it is to do forecasting value added exercise and directly compare the gains in forecasting performance against the additional computational cost, and potentially being in a position to compare the monetary value of the additional forecasting performance against the monetary value of the computational resources needed.
Well, I know a lot of textbook statisticians will follow some procedure like AIC or BIC and use that as the rule of thumb for deciding on model selection. How do you contrast your approach in light of techniques like those?
In this particular paper, we still rely to information criteria, and in particular, we use the corrected version of AIC, corrected for small sample sizes, to select between the reduced family of exponential smoothing models or the reduced family of ARIMA models. So still, this is in line with that. But equally, I'm working now with my colleague Enno Simpson, my co-author Enno Simpson, and we are working together on a new exciting way to select between different models. We call this forecasting by representativeness, and effectively what we do there, we are trying to see how the produced forecasts match or not match the patterns of the past. So effectively we try to do some sort of an asynchronous comparison between the forecasts, the out of sample forecasts, with the in sample data, rather than relying to asynchronous comparison of the in-sample fit forecasts with the in-sample data.
It seems like a much more scientific way of validating it then. Is that a fair way to look at it?
In essence, it's whatever the teacher would tell us, that is, check the output of the statistical software, right? So once you have the output of the software, once you have the forecasts, do not directly blindly use them. Effectively check the output and see if the output is in line with the data you have. This is more or less the case. And in this sense, if you wish, we can see that several times we can avoid using forecasts that are explosive, such as forecasts produced by multiplicative trend models.
Could it be that there is some great demand for multiplicative trend models, but it just so happens the M competitions are, a subset of all possible time series problems, and so are all the other data sets somehow. Is there a data set out there that people are ignoring or haven't discovered where it's going to demand techniques like that?
I think in our analysis, we used data from three competitions, M3, M4, and M5. And in particular for the data from the M3 and M4 competitions, this is a massive data set of 100,000 time series. And it has been shown that it has been quite representative. And it includes data from different categories: micro, macro, finance data, industry data, demographic, and so on and so forth. So overall, across all of these data, what we propose works. However, I can see the point that it might be the case that in some particular cases, multiplicative models may still be needed. You can consider, for instance, the very early stages of the life cycle of a product, where still the demand increases exponentially. But however, you cannot apply exponential smoothing models with multiplicative trend forever, because at some point the demand will saturate, and at some point we will reach the maturity phase and we will need something with dumb trend or even level only models. Yes, in particular cases, multiplicative models may still be needed. However, I think the set of 8 exponential smoothing models that we give here, that we offer here, we propose, is generic enough to be applicable in a wide range of models. We don't, though, exclude that a different subset, larger or smaller, could be more appropriate in particular cases.
For people looking to publish papers in the future, I assume we're still going to see some of the standard metrics, accuracy, MAPI, this kind of thing. Do you have any recommendations for how people should maybe publish alongside of those metrics to emphasize that they paid close attention to the cost of error?
Yes, I think one of the most obvious ways, which I've mentioned, is about contrasting the forecast value added against the reduction or increase in computational cost. That's, of course, one way, and potentially making some trade-off curves around this. But, of course, we have to still remember that there's a third aspect there, which is the cost of the forecast error. Not the cost of producing the forecast, but effectively what the forecast will translate into, and that is the utility of the forecast. And when we talk about the cost of the forecast error, here comes the M6 competition, which is currently in design. What we do in the M6 competition, we will deal with predicting stocks and ETFs And we will ask participants to provide their forecasts, but we'll also ask participants to submit their portfolio selections. So we will directly measure the accuracy of the forecasts and balance it trade-off against the performance of the portfolios, the investment performance effectively. And I think this particular aspect, the utility of the forecasts, is something that is generally very hard to approach. If you consider demand settings and inventory forecasting, it is the most straightforward solution would be to measure the inventory holding cost and potentially the backlog cost and then the customer service level and do some trade-off around these quantities. However, at any point, we need to do some very hard assumptions because, for instance, the backlog cost is something that we don't really know. What is the cost of not fulfilling the demand of a customer? If somebody walks into a supermarket and they don't find what they need, what is the impact of that? Do they go to another supermarket or do they come back the next day? Maybe they tweet something about it and then they make a negative impression out of it. So we don't know exactly how to measure this backlog cost effect, the customer dissatisfaction, and this is something that is quite significant.
Yeah, it's a very interesting problem. I can sympathize with how challenging when you don't have the counterfactual to work with. But anyway, we've touched a little bit on some of the things you're currently working on. To wrap up, I'd love to know a little bit more about what you're excited about for research going into the future.
One article that I am currently preparing, it's a collaboration of 80 academics and practitioners, including myself, and this is effectively encyclopedic approach of forecasting. We call it forecasting theory and practice, and it consists of two big parts, the forecasting theory, and then we have also the forecasting practice, and we show in how many different contexts forecasting is applicable. I'm quite excited about this project. Effectively, each of the co-authors has contributed with two subsections, one in the theory and one in the practice. And it's a nice collective effort which we have submitted for publication in the International Journal of Forecasting. And once it's out, we are aiming to translate it, to transform it into an open source solution which is going to be updated periodically and be an actual encyclopedia for forecasting.
It's very exciting. Please keep us posted. I look forward to covering more on that as it progresses. Well, Fotios, thank you so much for coming on the show and sharing your work.
Thank you so much for the invitation, Kyle.
That concludes another installment of Data Skeptic Time Series. Our guest today was Fotios Petropoulos. Thanks to our sponsors, Dataiku and LinkedIn. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Pulich.